Hey, our topic today is continuity. So looking at different types of continuity, any constraints that we need to guarantee continuity, and then the intermediate value theorem. So looking at types of discontinuities, we'll talk about continuity by talking about other times a function isn't continuous. So visually, looking at the graphs, you see this one where there's a hole in the graph at the endpoints and in the middle. Here we have two very discrete line segments. Here we have kind of an absolute value like in V, but then there's this point down here where the function can exist. So there's an existence, but the existence is away from the graph, so it's still discontinuous. Then here we have two curves. Looks like we have a vertical asymptote. We have the function going down, and then the function on the other side going up. So 4 different cases of discontinuities. For the criteria for continuity, we're looking at a test you can do that kind of shows how these 4 don't quite work. So the criteria for discontinuity, this is the 3-limit definition. If they ever ask you to show that the function is continuous at a point or at an interval, this is the test you want to do, these 3 steps. And for these 3 steps, we're going to say this is at x equals c. Alright, so we're looking at continuity at a point. And then continuity at a point, a single point, can be generalized to continuity over an interval. So here's the first step for continuity. This is big. This is so big you're going to be like mind blown. Whoa. Alright? So first, f of c must exist. I know, mind blown, right? I mean, but it is a big crux. Like, if you want something to be continuous, the something itself has to be there in the first place. So while it's kind of an underwhelming, like, what's the first step? Oh, that just the function exists. It is necessary for the function to exist. And step 1 is kind of the algebra. Okay, what the function is. Does the function exist at a point? Step 2, we're going to go more along the calculus route. The limit as x approaches c of f of x that also must exist. So step 1, kind of the algebra. Step 2, the calculus. And then in step 2, this kind of gives you quite naturally, step 2 gives you 2 things you got to look at. For a limit to exist, the limit of f of x as x approaches c from the left has to equal the limit of f of x as x approaches c from the right. So those 2 things have to be equal to each other. And my notation, what I'll use, I'll do an equal sign, kind of a question mark. I do that to remind myself, like, hey, I gotta address, do they equal? That's the question I'm asking myself. do they equal each other? If the two sides equal each other, if you have convergent behavior, then the overall two-sided limit does exist. And then lastly, for step 3, there's step 1, does f of c exist? Step 2, does the limit as x approaches c exist? Step 3, again, mind blown. We're going to start with a mind being blown, and with blowing out anything else that's left in there. F of c and the limit of f of x as x approaches c. Are those equal to each other? So your 3 steps really. First step, does the function exist? Second step, does the limit exist? Step 3, are they equal? Did you get the same answer all the way through? The nice thing about this test, you can stop it whenever you fail. So whenever the test doesn't work, when your work doesn't show what you needed to show, you're done. Whether you fail at step 1 or 2 or 3, once you fail, once you show that it's not continuous, you're done. Alright? Now again, talking about continuity by talking about discontinuities, how those happen. How those happen, and if they don't happen, then it must be continuous. So removable versus non-removable. So removable discontinuities were what we looked at a few sections ago with evaluating limits analytically. So removable, literally, can you remove a problem factor? So if you have a limit as x approaches 3, let's say in the top you have x minus 3 over x minus 2 and x minus 3. So that problem factor, the x minus 3, if you can literally remove that, that's the removable discontinuity, and you can fill the hole. So your original function, something like that with a hole in it, but the other function you find that is the same function at all but one point, then it goes through and fills that hole. That's the removable discontinuity. A non-removable is, to kind of put it tongue in cheek, a non-removable is something you can't remove. But it's something like a vertical asymptote, where there is no problem factor that you can get rid of. So, looking at your parent rational function, 1 over x as x approaches 0. So there's nothing to factor out or cancel, and as a result, it's a non-removable discontinuity, the hole you can't fill. With that here, okay. So, example 1, discuss the continuity of each. Be sure to do those 3 things. The interval over which it's continuous, the values of x which make it discontinuous, and then classify any discontinuities. So let's kind of zoom in down here. Well, where is that? There you are. Okay, zoom back in. Alright, so a parent rational function. Kind of think in your head. Looks a little something like that. Obviously, that's kind of a poor representation, but it's good enough, okay? So, step 1, state the interval over which is continuous. Now, with those two branches, I cannot find a good spot for this. Okay, let's put it there. See how that goes. So the two branches are pretty intact. This one over here, this one over here. The only problem is at 0. So this function is continuous on the interval -infinity to 0, and then from 0 to positive infinity. Okay, just at that 1.0 we have discontinuity. Everywhere else it's continuous. Step 2. Where is it discontinuous? What values of x? Well, based upon our intervals, it is discontinuous. And you're probably already thinking it. It's discontinuous at x equals 0. Just a single point. And step 3, is it removable or non-removable? Well, 1 over x has no factors you can cancel out. So that discontinuity would be non-removable. And kind of why is it non-removable? Non-removable because of a vertical asymptote. You really don't need to include that. They only wanted you to classify as removable or non-removable. Then what type? What is the note? So why not have that? So when you refer back, you have something written down. Example B. Let's start by, I'm going to move in this. Okay, so let's start the problem by noticing that this is a polynomial rational function. So let's factor the bottom. That's a quadratic that can factor into two sets of parentheses. So kind of x plus 4 in the top, not too much you can do there. In the bottom, two sets of parentheses, what numbers multiply to -24, but add to -2. So x minus 6 and x plus 4. And now we have a common factor in the top and bottom. That common factor is also kind of a problem. You can get rid of it. Just left with 1 over x minus 6. So our 3 steps. Step 1, it's continuous. Now, this is kind of tricky, okay? If you look at the factors in the denominator specifically, x equals 6 and x equals -4 are two discontinuities. Now, one is removable, the other is not, but they're both still discontinuities. So our intervals have to reflect that. Nope. Want the pen, there you go. So from -infinity up to -4. From -4 to 6. and then from 6 to positive infinity. Alright, so 2 discontinuities, yeah, one removable, the other's not, but you gotta include both because they're both still discontinuities. Step 2, identify what x values make it discontinuous. We kind of had to do that already to address step 1, so really just formally writing it down. Discontinuous at x equals -4 and 6. So now step 3 for each of those, are they removable or non-removable? So x equals -4, which is corresponding to the factor we could cancel out, so the factor we could quite literally remove. So x equals -4 is removable. And x equals 6 is non-removable. Then gotta add a little additional information, so y. Now x equals -4 is a hole in the graph. X equals 6 is a vertical asymptote in the graph. So the 3 steps for continuity, really the definition of continuity, and then example 1 kind of asking you to do some things around continuity, discontinuity, what types of discontinuities they are. On the second page, look at those, work on them, check my completed notes online. Especially for example 2, this comes up a lot, it's kind of cool. You have ax plus 1 on the top, and the second part, ax squared minus 1. And really looking at continuity at 3. Now you have 2 variables, a and x. Of those 2, do you have a value you could plug in for one of them? Okay, I want to kind of plant that thought in your head. Now the last thing for this unit, the intermediate value theorem, which again I like because there's a pretty simple way to visualize it, okay? Imagine when you go into high school, you are about 14 years old. When you graduate, you're about 18 years old. So from the time you enter to the time you leave, 14 to 18. Now, I don't know exactly when it happened. I technically don't know how many times it happened. But I can guarantee at some point in there, you were 16 years old. That is the intermediate value theorem, alright? Kind of put simply. But if f is continuous, which time, for our purposes, time is continuous. So we have continuity on a closed interval a to b. So from the time you're a freshman to the time you're a senior. And k is any number between f of a and f of b. There is at least one number c in a to b such that f of c equals k. So if the age 16 is between 14 and 18, then there must be some point in your high school career when you were 16. okay? Visually, kind of looking at this, from A to B, from f of A to f of B. So in this interval here, can you trace those over? There must be some value that works within the inputs and within the outputs. Now, how many times that happens? Who knows? This case could be 3, alright? But we know a guarantee it happens at least once. So an example I kind of give is to say, hey, draw a quick coordinate system here. Here's my first point. Here's my second point. And I kind of make a challenge to the class. I guarantee no one can continuously connect this point to this one without passing that dotted line. If you're going to connect them continuously, you have to pass it at least once. So example 3, use the intermediate value theorem to show that the polynomial function has 0 on the interval 0 to 1. So 0, just to be clear what we're looking for, a 0 is where a function crosses or touches the x-axis. So let's see whether we can guarantee that this happens between 0 and 1. So let's start by looking at our endpoints, f of 0 and f of 1. Now f of x is a cubic function, so it's continuous everywhere it will behave. So we have passed that hurdle for the hypothesis of the intermediate value for the hypothesis of the intermediate value theorem. So plugging in 0, 0 cubed plus 2 times 0 minus 1, we get negative 1, which is below the x-axis. So on our interval, we're starting below the x-axis. If we plug in 1, so 1 cubed plus 2 times 1 minus 1, we get 2. And believe it or not, 2 is above the x-axis. So if we're starting below, and then we're going above continuously, I think we're going to have to cross the x-axis itself at least once. So the language I'm going to use for this problem, make sure you write this down because the language I'm using is good language. I think it can really guarantee you points on the exam. This exam is all about guaranteeing how many points we can accumulate, okay? Chances are you're not going to earn an A on this exam, or a B or a C, but how many points can you get, and then the curve will give you a 1, 2, 3, 4, 5. So f of x is continuous on the interval, the closed interval 0 to 1, and this interval notation, if you remember, is the same as 0 less than or equal to x less than or equal to 1, so inclusive intervals. So f of x is continuous. Therefore, f of x has at least one zero on the open interval 0 to 1, and open interval, I mean our endpoints f of 0, f of 1 are not themselves zeros, so we don't have to include them. And this is all guaranteed by the IVT, the intermediate value theorem. Okay, so looking at how to use the theorem, the existence theorem, and then what language you get to use to show you're fulfilling the hypothesis and then making a valid conclusion.